Today we'll derive the Bekenstein-Hawking entropy of a black hole from the Schwarzschild solution. We do need a bunch of prerequisites. The first is that the Euclidean path integral, the Euclidean thermal path integral, which is nothing but the partition function, which is a trace over exponential minus beta h over all the Hilbert space, is equal to the path integral over our fields with periodic boundary conditions with a period beta, which is the inverse temperature. This is because minus beta is a propagation over an imaginary time I beta. So the thermal partition function is given by a Euclidean path integral on the circle. The second prerequisite is that you know the Hawking temperature, which is 1 over 8 pi g Newton times the mass of the black hole. The third prerequisite is that we have a Euclidean action, which is equal to an Einstein-Hilbert term, plus a Gibbons-Hawking York term in the case where we look at manifolds with the boundary and Dirichlet boundary conditions for the metric. This Gibbons-Hawking York term contains an induced metric h, boundary coordinates y, as well as an extrinsic curvature k, which is nothing but the covariant derivative of a unit normal vector to the boundary. So given these prerequisites, the Euclidean path integral, Hawking temperature, and the Gibbons-Hawking York term, we can start deriving the black hole entropy. So the first observation is that if we evaluate the action on a solution, then the Einstein-Hilbert term in the action, namely the first term, which is proportional to r, is 0 because of the vacuum Einstein equations. So the bulk term is not going to contribute to our Euclidean action or the saddle point approximation to the path integral, but only the boundary term will contribute. So only the boundary term contributes. Now, if we draw the Euclidean black hole, it looks like a cigar. Where the circle direction is the thermal direction of radius beta, and where we have for each point on this drawing, we have an extra S2, which is corresponds to the horizon of the black hole. Now, when we compute the boundary term, we'll get infinity, and we'll subtract a reference spacetime, which is nothing but the flat spacetime. So if you wish, we're comparing the cigar geometry of the Euclidean black hole with a flat space geometry, which we use as a regularization. Of course, the flat space geometry is also compactified at the same temperature beta as the black hole in order to match the asymptotics. So what we will actually compute is a regularized action, which is the Gibbons-Hawking term on a regularized spacetime, which we cut off at R0. Integral of square root of the term of the induced metric times k minus the action for the spacetime we use to regulate, in this case flat space. So let's recall the metric of the Schwarzschild black hole solution in order to be able to compute the extrinsic curvature, etc. So the radius, the Schwarzschild radius is 2gm. We have a compactified Euclidean time coordinate, tau. We have the same factor for the radial metric. And then we have the two-sphere. So this is the Schwarzschild solution. So now we need a unit normal vector. So to the boundary. So this will be in the radial direction because we're going to fix r equal r0. And the unit normal vector will be n, which is equal to nr times dr then. And since it needs to be unit, we take it to have the square root of the metric component grr as its normalization. Then if we compute its norm, it's 1. And then to fix conventions, we actually needed to point inward. Then we can start computing the extrinsic curvature, which is nothing but the covariant derivative of this unit normal vector. And this equals 1 over square root of the metric times dr times the square root of the determinant of the metric times nr, like this. So then we need to compute this. So since the angular parts cancel, we'll get 1 over r squared here, dr r squared nr, which is 2 over r nr plus dr nr. So then we need to compute this. So we'll get 2 over r times nr plus dr of nr, which is going to be minus, and then the square root times a half minus a half times 2gm over r squared. So then this is nothing but 2 over r times nr plus gm over r squared times 1 minus 2gm over r times nr, which in turn is equal to 2 over r plus gm over r times r minus 2gm times nr. Okay. Now we still need to compute the integral d to the third x square root h k, the extrinsic curvature. So square root h, well, what is the induced metric? So the induced metric, the s square induced, is 1 minus 2gm over r tau square. No dr part anymore, and then we'll take it at r0. So then we have this induced metric on the boundary surface. And so the determinant, or the square root of the determinant, is r0 squared times sine theta, which is hiding in the metric for the two-sphere, times the square root of the prefactor for the tau component. Very good. So then this integral is nothing but, well, the integral over the sphere, which is going to take into account the sine theta. So that's going to be a 4 pi times the integral over the circle, which is going to give us a factor of beta. And then we have all of these factors depending on R naught. So R naught square. Then we have 1 minus 2gm over R naught, the square root from the determinant of the metric, but then another square root coming from the NR, and then a minus sign coming from the NR. What else? Then we have the extrinsic curvature factor 2 over R naught plus gm over R naught times R naught minus 2gm. All right, so then if we now multiply a few things, we're going to multiply R naught squared through, so we get R naught minus 2gm when we pick a factor of R naught here, and then we multiply also in the last factor, so plus 2gm over R naught minus 2gm. But then we multiply the R naught minus 2gm through, and we get minus 4 pi beta times 2 R naught minus 4 gm plus gm. And this is nothing but minus 4 pi beta 2 R naught minus 3 gm. So far, so good. Now we need to repeat this for our reference spacetime, of which we need to recall that it needs to match asymptotically with our cigar spacetime. And therefore, we take the reference spacetime to also depend on the mass. So it is now a flat spacetime, but with an appropriate radius for the thermal circle. And if we then repeat the calculation, we will find that the integral of the extrinsic curvature in this case is very similar, except that we have a factor of minus 2 gm. So then calculating the Euclidean action for these saddle points, or difference of the Euclidean action for these saddle points, we get 4 pi beta times 3 gm minus 2 gm. So we get just 4 pi beta gm divided by the prefactor of the Gibbons-Hawking York boundary term. This gives a total of beta m over 2. Now we want to express this in terms of beta in order to, which is the inverse temperature, in order to be able to apply formulas from thermodynamics. So we had that the Hawking temperature was 8 pi gm, so the inverse was 1 over 8 pi gm. So the inverse Hawking temperature is 8 pi gm. So if we plug this formula in for the mass, we get beta over 8 pi g. So Euclidean action here regularized is beta square over 16 pi g. Now, the Euclidean action is the negative of the logarithm of the partition function in this saddle point approximation. Therefore, the logarithm of the partition function is minus beta square over 16 pi times g Newton. Now, the entropy from thermodynamics is nothing but 1 minus beta d beta of the logarithm of the partition function, which, given the formula above, is nothing but beta square over 16 pi g. Now we want to express this in terms of the area of the horizon. The area of the horizon is just a two-sphere formula, 4 pi times the radius. The Schwarzschild radius is 2gm. So we get 16 pi g square m square. So if we express the entropy in terms of the mass again, using the formula for beta, we get we get 64 pi square g square m square divided by 16 pi g, which is nothing but 4 pi g m square. So if we express this in terms of the area, we see that the entropy is equal to the area divided by 4 g Newton. This is indeed the Bekenstein-Hawking entropy. So here we've derived it from a Schwarzschild solution using the idea that the gravitational path integral, or the gravitational field, is very much like a thermodynamical field. So this begs the question, if this is a thermodynamical description, then what is a microscopic statistical mechanical description of this entropy? And this is a central question in quantum gravity.